Now, there are two key algorithms that we are going to be looking at. We have what is called the Dexterous Algorithm, DIJK59. Then we have the Bellman-Ford algorithm. Now, I'll be taking you through the algorithm, then we'll solve an example. Now, so what is Dexterous algorithm all about? It's still about finding the shortest path from a given source node to all other nodes by developing a path in order of increasing path length. So in the algorithm, we have big N, which is a set of nodes in a network. We have the S, which is the source node where the packet is moving from. Then we have T, which is the set of nodes so far incorporated by the algorithm. So per the algorithm, we calculate a Wij. Now Wij is the link cost from node I to node J. Now if we are calculating Wii, meaning that we are moving from one node to itself, then the cost associated with that is 0. And if we are moving from node I to a certain node J, if the two nodes are not directly connected, then we say that the cost associated with that is infinity, or it's large, it's positive infinity. Now, Wij needs to be greater than or equal to 0. Here, if the two nodes are directly connected, then we expect that their cost is either 0 or greater than 0. We'll look at Bellman-Ford that deals with negative cost or negative weight. Then we'll calculate L of N, which is the cost of the least cost path from source or from the node S, which is the source, to a node N or the currently known node. Now at the termination, L of N is the cost of the least cost path from S to N. So let's look at the steps. Step 1 is initialization. So T is set to a set of S. That is the set of nodes so far incorporated, which consists of only source nodes. Now take your time and go through the algorithm. I'm going to take an example that will simplify these algorithms for us in a bit. So let's take an example of Dexterous algorithm. Now here we have our nodes N1 to N6, and we can see the cost, the various costs associated to the link. Now we want to find the shortest path from node 1 to node 6. The good thing about Dexterous algorithm is that by the time we are done finding the path from node 1 to node 6, we would have calculated the path to every other node. Now let's see how that is done. We'll start off by drawing our table. And this we will put node 1, node 2, node 3, node 4, node 5, and node 6. Now, our starting node is node 1, and that's why this has been arranged that way. If your starting point is node 2, then you arrange it likewise. So it means we would have to start node 2, probably then node 1, node 3, node 4, node 5, node 6. Now, if node 1 is going to itself, we represent its cost with 0. You remember the initialization. So to initialize this, we set node 1 to 0, the cost at the node. So it means node 1 has a cost of 0. Then to every other node, we set it to infinity. So this is the initialization. Now, of course, node 1 to node 1, it means we have visited node 1. So we'll come down and do 0 node 1. Then we'll put a box around it, indicated that we've already visited node 1. Now, from node 1, if we are going to node 2, we want to calculate the cost of going to node 2. Per the algorithm, we will take the cost at node 1, add it to the cost of the link, and that will give us the cost at node 2. So if I take node 1, the cost at node 1 is 0. The cost of going to 2 is 2. So 0 plus 2 is 2. Now I compare that value to the current state of node 2. Remember, initialization, the value of all these is infinity. So I add 0 to 2 and I compare that value to the current value at the node. Now 0 plus 2 is 2. Now 2 compared to infinity, 2 is smaller than infinity. So I'm going to put 2 here. And where is it coming from? It's coming from node 1. So I do a subscript node 1. So it means now I know the cost at node 2, which is 2. Now let's look at from N1 to N3. Now from N1 to N3, there is a direct link this way to N3, and that is at a cost of 5. So it means I can reach N3. Now 0 plus 5 is 5. 5 compared to infinity, 5 is smaller. So I have 5, and this is coming from node 1. Now let's take from N1 to N4. N1 to N4, there is a direct link at a cost of 1. So 1 plus 0 is 1. 1 compared to infinity, 1 is smaller. So I have 1 here coming from node 1. Now let's go to N5. From N1 to N5, there is no direct link to N5. So we'll still repeat the infinity. Remember, the algorithm said that when Wij does not have a direct link, then we put an infinity there. So from N1 to N5, we have infinity. We can say the same for N1 to N6. So we have infinity this way. Now, we have completed the first part. Now, the next thing is to look through the values and see the smallest. Whichever is the smallest, we repeat that value. So, for instance, if I look through this, 1 is the smallest. So, I repeat 1 down here, then circle it or put a box around it. Then I'll put that value here. Don't forget, here we're from N1. So, I have N1 here. So, here we have N4. So, it means that we are currently standing on N4. So, this is N4. It means we know the current value of N4. So, I can update this infinity and put here 1. So, that is the cost at N4. And that is coming from N1. Okay? Hope you are following. Now, from N4, because we have already circled N1, we are not going back to it. You can even check. From N4, there is no link going back to N1. So we go to N2. Is there a connection between N4 to N2? Now N4 is this way, N2 is that way. there's no connection, so we still repeat the value that was already there. What about N4 to N3? N4 to N3, yes, there is a direct link to N3 at a cost of 4. So we'll add 3 to 1. We'll add this 3 to 1, the cost of the link to 1. And that is 4. Then we'll compare that value to the current value at 3. So the current value at 3 was 5. And this is what is showing. So 3 plus 1 is 4. And 4 compared to 5, of course, 4 is lesser. So I put 4 here. And this is coming from N4. It means that's the predecessor. Okay? Now, from N4, we go to N5. So from N4, do we have a connection to N5? Yes. At a cost of 1. So 1 plus 1 is 2. 2 compared to infinity, 2 is smaller. So I pick the 2, and this is coming from N4. Now from N4 to N6, we still don't have a direct link. So I repeat the infinity. Now we are done with that process. Now we have the smallest value again to be 2. But you can realize that we have 2 of the 2's. Now you can pick the first one. When you pick the second one, it also works fine for you. So I'll pick the one under N2. So 2N1. It means I've visited N2, or I'm currently at N2. So from N2, is there a connection to N3? Yes, there's a connection to N3 at a cost of 3. But the cost at N2 is 2. So 2 plus 3 is 5. Now 5 compared to 4, 5 is greater. So I will still repeat the cost there. Now N2 to N5, is there a direct link? No, there's no direct link. So I still repeat the cost there. N2 to N6, is there a link? No. So I repeat the infinity. So far you have seen the trend. So we look for the smallest, sorry, this is supposed to be 4. So we look for the smallest value again. That is N5. So at 2. So I repeat this, and I put the box around it. Then I repeat, or I put my N5 this way. So it means currently we are at N5. Now N5 to N3, is there a link? There's no link going to N3. So I still maintain the value of N3, which is 4. Is there a link to N6? Yes. I can go to N6 at a cost of 2. But the current value at N5 is 2. So 2 plus 2 is 4. 4 compared to infinity is 4. So this is coming from N5. Okay, so now I have 2 of the 4s. I can choose this one. Once I choose that one, I circle that box. It means now I have N3. Now, from N3, what is only left is N6, because we've already circled N1, N2, N4, N5. So I can move from N3 to N6, and that is costing us, the link cost is 5. Now the cost at N3, of course we've updated this to 4. So the cost at N3 is 4. 4 plus 5 will give us a 9. And 9 compared to the 4 here will still maintain the 4. I guess you are following now. Now we are only left with N6. And of course we repeat this and we circle it. It means that we have now visited N6. And that will bring us to the end of the computation. Now let's understand how to read the table. We said initially that we want to see the shortest path from N1 to N6 and at what cost. Okay? Now this is how we read the table. The destination is N6, so this is N6. Now, the cost of going to 6, the shortest or the least cost of going to 6 is 4. So whatever the path is, we're expecting that it will cost us 4 to get to 6 from N1. Now let's trace the path. So our destination is N6. Now, N6 came from N5. So this is N5. So we just trace and go to N5. So I'll put N5 here. It means that to get to N6, I need to come from N5. Now this is N5. Now to go to N5 too, I need to come from N4. Notice what we are using. We are using the predecessors. So this is N4. So I have N4. Now, so I trace N4. This is N4. N4 came from N1, which of course is our starting node. So I have N1. And this gives us the shortest path from N1 to N6 at a cost of 4. Let's read that from the table. So we have N1. Now, from N1 to N4 it will cost us 1. Okay? Now from N4 we are supposed to go to N5. This is N5. So we move, so we are follow me. We are moving this way. Then from N4 to N5, also at a cost of 1. Then from N5 to N6, and here is at a cost of 2. So you realize that 1 plus 1 plus 2 will give us 4. Now, from the table we can read any other node. So let's say I'm moving from N1. I want to find the shortest path from N1 to, say, N5. So we are moving from N1 to N5. We'll take the same principle. Our destination is N5. So from N5, it will cost us 2. So we already know that the cost from N1 to N5 is 2. But now let's look at the physical path. So to get to 5, we need to go to 4. Or we need to come from 4. Now from 4, we can just come directly from N1. So the shortest path from N1 to N5 will be N1, N4, N5. And we can still trace that. It means we have N1 to N4, then N4 to N5. And the cost is 2. So this brings us to the end of Dexterous algorithm.